Okay, let us do corrections of exercise 4 on page 121. Right, we're starting with number 1. It says methanol is sealed in a closed container and reaches equilibrium after 5 minutes at a temperature of 400 Kelvin according to the equation. So you have 2 methanol giving you 2 carbon monoxide plus 3 hydrogen gas, and this is the graph. And can you see this is the reaction rate versus time graph. Now remember we said there's always 2 graphs in equilibrium. The one is concentration, the one is reaction rate. So when you're looking at the graph, make sure you know which one you're looking at. Don't assume it's concentration because it can be rate of reaction. So in this one, it's a rate of reaction graph. So always make sure you know what graph it is before you start answering the questions. Okay, it says here after 10 minutes, the temperature increased to 500 Kelvin. The graph shows the change in reaction rate versus time lapse of 20 minutes. Number 1.1, write down the balance equation for the reaction that is represented by the stipple line. Now, in a rate of reaction graph, you have 2 graphs. One is for the forward reaction, one is for the reverse reaction. Now, the forward reaction is always the one decreasing. The reverse reaction is always the one increasing from 0. So the stipple line is the reverse reaction, which in this case, if you swap it around, it becomes 2 carbon monoxide plus 3 hydrogen, giving you 2 methanol. Okay. Right, 1.2. What is the reason for the decrease in the reaction rate as represented by the solid line between 0 and 5 minutes? So between here and here, what is the decrease in the reaction rate of the solid line? Now the solid line is showing you the forward reaction. So why is the forward reaction decreasing between 0 to 5 minutes? Now first of all, when you have a forward reaction, it means you have reactants and you're making products. Now, because you're making products, the reactants are becoming less, which means if they're becoming less, their concentration is decreasing, which means if concentration decreases, the rate of reaction will decrease. So because initially you are getting rid of reactants because you're making them to turn into products, the rate of reaction will decrease because concentration of reactants are now less. And also, because you're going to reach equilibrium, the forward and the reverse reaction needs to become equal, which means the forward reaction has to decrease, the reverse reaction has to increase, so that the lines can touch each other. And when they touch each other, the rate of reactions are equal, which means equilibrium has been reached. And if you look at this graph, can you see we have equilibrium twice? We have equilibrium here where the graphs are touching. Then we have some kind of a disturbance. Then we have equilibrium again at the end. Right, let's look at the next question. Question 1.3. Is the reaction that is represented by the stipple line exo or endothermic? Explain the reaction referring to the graph. So the stipple line, remember we said, is the reverse reaction. And they're asking us, is it endo or exothermic? Now, if we look at this graph, can you see that the reverse reaction, all of a sudden, it became less. And the forward reaction, when we had a disturbance in equilibrium, the solid line, it became more. It spiked up, which means the forward reaction has been favored. Now, initially, they said that the temperature increased to 500 Kelvin. So they increased temperature. Now, increase in temperature favors endothermic reaction. Now, if you can see this graph, the solid line spiked up, which means the forward reaction has been favored. So if you increase forward reaction, if you increase temperature and the forward reaction was being favored, it means the forward reaction is endothermic, because increase in temperature favors endothermic reaction. And if the forward reaction is endothermic, it means the reverse reaction has to be exothermic. So the answer is exothermic. Right, 1.4, what is represented by the horizontal part of the graph between the 15th and 20th minute? Now, anytime you have a rate of reaction graph and the graphs touch, it means equilibrium. So between 5 and 10 minutes, the graphs are touching, so it's equilibrium. Again, between 15 and 20 minutes, the graphs touch, so again, it's equilibrium. Right. Then we have here 1.5. How does the value of Kc compare at the 8th minute and the 18th minute? Answer only greater, smaller, of this or the same. Now we said the only thing that affects Kc is temperature. And if you increase temperature, it favors endothermic reaction. And since this reaction, the forward one, is endothermic, it means increasing temperature is going to favor the forward reaction. So we're going to make more products. And we know Kc is equals to products over reactants. So if you increase products, it means Kc will be more. So the answer is greater. Right, 1.6, after 20 minutes a catalyst is added. What will the graph look like now? Now, adding a catalyst, remember we said it makes no change in the concentration, no change in anything. The only thing it does is makes the reaction rate faster. Now, since we are looking at reaction rate graph, if you have a catalyst, it's just going to make the rate happen faster. Now, if you look on page 121 at the top, if you add a catalyst, this is how your graph should look. So this is what your answer should be. It should be a certain rate in the beginning, all of a sudden the rates increase, and then you have a higher rate at the end. Right, let's move on now to question number 5. Right, it says here, the graph shows the concentration of all three substances of the following system versus time. You have the reaction hydrogen plus iodine giving you hydrogen iodide. Now again, first make sure you know what graph you're looking at, and here we're looking at concentration versus time graph. Okay, so make sure you establish that first before you carry on. Right, it says 5.1, after how many seconds does the reaction reach equilibrium for the first time? Now, if you have a concentration versus time graph, if the graphs are parallel, that's when equilibrium is reached. For a reaction rate graph, if the graphs are equal, then equilibrium is reached. So since this is a concentration versus time graph, we are looking for parallel lines. Now, the first time it reached parallel lines is here and here. So it's basically at 10 seconds. So it took 10 seconds to reach equilibrium. Okay, and if you look here again, we had some kind of a disturbance, then again it was parallel, so again equilibrium, then we had another disturbance, and then again equilibrium with parallel lines. But the first time was at 10 seconds, so the answer is 10 seconds. Right, 5.2, write the equilibrium expression for this reaction and calculate the equilibrium constant. Remember, Kc is equals to concentration of products over concentration of reactants. So it's going to be Hi concentration squared divided by H2 times I2. And remember, every time you write concentration, you put square brackets. Right, and then from the graph, we can actually find the values of it. And remember, Kc is an equilibrium constant, which means you need to use equilibrium concentrations, not just any concentrations, only the concentrations at equilibrium. So we're going to choose the first equilibrium, which is at 10 seconds, and use the concentrations at 10 seconds, not anywhere else. So for Hi, the concentration, Hi is the solid line. So the concentration at 10 minutes is about 6.4. So it's 6.4 squared divided by H2 concentration. H2 is about 0.8, and then I2 is also 0.8. And that will give you Kc of 100. Now remember, please, when you work out Kc, you have to use equilibrium concentration, not any other concentration, which means you need to use the concentration where the parallel lines are. Okay, right, and can you see this Kc? It's 100, so it's greater than 1, which means you have more products and the forward reaction is being favored. Right, 5.3, give an explanation for the change that takes place at time is equals to 30 seconds. Now, if you look at 30 seconds, can you see what happened? You have all of a sudden a drastic decrease in this graph, and this graph is Hi. So you drastically decreased Hi at 30 seconds. So what could that have been? So since it's a concentration versus time graph, it means the concentration drastically decreased. So Hi drastically decreased, which means you either took it out. So if you're taking it out, it means now the forward reaction is, because you're removing product, it means now to overcome that disturbance, you need to favor the forward reaction so you can make more product, and then the reactants will decrease. So since you have decreased product, the forward reaction is favored, which means you're going to make more Hi. And then after this, can you see that Hi increased slightly? Because the forward reaction has been favored, which means H2 and I2 is going to decrease slightly. And can you see here? it decreased slightly, both of them. Right, so that's what is being shown on the graph at 30 seconds. Then 5.4, if the change at time is equals to 35 seconds is caused by the rapid increase of the temperature of the system, report if the system is endo or exothermic. Now they're saying at 35 seconds you had a rapid increase of temperature. Now 35 seconds, can you see what's happening here? HI is decreasing and H2 and I2, the reactants, are increasing. Now the only time H2 and I2 will increase is if you're favoring the reverse reaction, because H2 and I2 is reactants. If you favor the reverse reaction, you're making more H2 and I2. So if you're increasing temperature and temperature increase is favoring reverse reaction, it means the reverse reaction is endothermic, because increase in temperature favors endothermic reaction. Right, let's carry on with number 6. It says, considering the following reversible change in a closed container, again you have hydrogen plus iodine giving you 2HI. The experiment is performed 3 times under different conditions. In each case, 0.5 moles hydrogen, 0.5 moles iodine reacted in a 1 decimeter cube container. The graphs of concentration versus time for this investigation are shown below. So you have graph A, which is obtained at 500 degrees Celsius, graph B, which is under the same conditions but a temperature of 600 degrees, so you increase temperature in graph B, and in graph C you have the same temperature 500 but different conditions than graph A. Right. 6.1, it says which factor is responsible for the difference between A and C. Now if you look at graph A, can you see you have products and reactants? The product concentration is 0.4. If you look at graph C, you also have the products and reactants. Product concentration is also 0.4. So we're seeing here that the concentration is not changing. Right. But if we look closely, can you see that we have equilibrium here where the graphs are becoming constant, and equilibrium is being reached at about 5 minutes. But if you look at graph C, you also have equilibrium reaching, but now it's coming at about 2 minutes. So only difference is when equilibrium is being reached. The one is 5 minutes and the one took less time, which is 2 minutes. So since you took less time, but the concentrations are exactly the same, it's both 0.4. You only change time and not concentration, and the only thing that can do that is when you add a catalyst, because remember, catalysts don't change concentration, they don't favor any reaction, they just make the reaction happen faster, which it takes 2 minutes instead of 5 minutes. Right, give an explanation. So that's just what I explained now. 6.3, is this reaction exothermic or endothermic? Now, if we look at graph A, it happened at 500 degrees Celsius. If you look at graph B, it happened at 600 degrees Celsius. Okay, now that means graph A has a higher temperature. But if we look at graph A and graph B, can you see the product concentration of A is 0.4 and of B is 0.38, which means when you increase the temperature, the product concentration became less. And why will product concentration become less? Only if the reverse reaction is favored. So if you're favoring the reverse reaction, you're making more reactant and you're making less product. So if the product concentration decreased, it means the reverse reaction was favored. So if you increase the temperature and the reverse reaction is favored, it means the reverse reaction is endothermic, because increase in temperature favors endothermic reaction. Okay, so if the reverse reaction is endothermic, it means the forward reaction, which is this H2 plus I2 giving you 2HI, is exothermic. Okay, so it's a long explanation, but that is exactly what it is. You just need to look at what is increasing. Is it products or reactants? If the products are increasing, forward reaction is favored. If reactants are increasing, reverse reaction is favored. Okay, right, let's go on to the last question, which is number 10. Right, number 10 is a nice question. It says here, the graph shows the number of moles of all 3 species of the system. So you have PCl5 giving you PCl3 plus Cl2, and here delta H is greater than 0, which means it's an endothermic reaction. Okay, and they're saying the reaction takes place in a 1 decimeter container at 500 Kelvin. Right, so you have this graph. Again, remember, we must see what graph we're looking at. So here we have number of moles times 10 to the minus 2. But remember, moles has to do with concentration. Concentration is equals to moles over volume. So if they're giving us moles and we have volume, this is basically a concentration versus time graph. So this, you will take it as a concentration versus time graph. Now, before we even start with the questions, remember in a concentration time graph, if the graphs are parallel, it means equilibrium is being reached. So here, graphs are parallel, so this is equilibrium. Then we have some kind of a disturbance, then parallel again, so it means equilibrium again. Another disturbance here, and then again at the end, parallel, so equilibrium again. Right, 10.1. How much time is needed for the system to reach equilibrium for the first time? Now, the first time we have parallel lines is at 10 seconds, which means it took 10 seconds for it to reach equilibrium for the first time. Right, 10.2. How do the rates of the forward and reverse reactions compare at the following times? Time is equals to 5 seconds. Now, if you look at here, time is equals to 5 seconds. This is the beginning of the reaction. Now, at the beginning of the reaction, the forward rate always becomes less and the reverse reaction always increases. And this is because if you're starting the reaction, you're only starting to make product. So all your reactant becomes finished, and since reactant concentration decreases, it means the forward rate will decrease. And since you're starting to make product, it means the product is now going to go back into reactant, so the reverse reaction increases. So just remember, always at the beginning of the reaction, the forward rate will always be slower, it will become slower faster, and the reverse rate will always increase faster. Right, next one. At time is equals to 20 seconds. Now, if you look at the graph at 20 seconds, can you see that it's equilibrium? And at equilibrium, both the forward reactions and the reverse reaction rates are equal. They are both the same. Right, at time is equals to 32 seconds. Now, let's look at what's happening at 32 seconds. Here's it here. Can you see we all of a sudden have Cl2 increasing at 32 seconds? Which means if Cl2 is increasing, Cl2 is a reactant, so if Cl2 increases, it means the reverse reaction is favored. So the reverse reaction will be favored, sorry, this is a mistake, and the forward reaction will be less. Okay, 10.3. Calculate Kc at 20 seconds. So at 20 seconds, we're going to calculate Kc. Remember, Kc is always using equilibrium concentration. So first of all, let us first do the equilibrium, the expression. So it's going to be products divided by reactants. So the concentration of Cl2 times PCl3 divided by PCl5, and then we're going to use the concentrations on the parallel lines because that's when it's equilibrium. So Cl2 is 0.025, PCl3 is the same because the lines are touching, so 0.025, and PCl5 is 0.1, and that will give you Kc of 0.62. Right, 10.4, calculate Kc at 75 seconds. So again, here 75 seconds, it's equilibrium again, but only now different concentrations. So we're going to have the same expression, but now Cl2 is 0.029, PCl3 is 0.018, and PCl5 is 0.017, and that will give you 0.031. Right, then they said 30 seconds after the reaction had begun, 0.01 moles of chlorine was added to the system. So they're telling us at 30 seconds, you're adding chlorine. So if you're adding chlorine, it's the same thing as increasing concentration of chlorine. Now they're saying, what will the effect be on the equilibrium constant Kc? And remember, we said the only thing that affects Kc is temperature. So since we're only changing concentration, there will be no effect on Kc. Only temperature changes Kc. Right, 10.6, explain with reference to Le Chatelier's principle why the number of moles of each species in the mixture changes between time is equals to 30 and time is equals to 35 seconds. Now let's see what's happening here. Between 30 to 35 seconds, can you see there is a spike in this solid graph which is showing Cl2. So the spike in Cl2 shows that chlorine has been rapidly increased. The concentration of chlorine has increased rapidly. And since chlorine is a reactant, it means if you're increasing it, you're going to favor the reverse reaction. So you will make more PCl5 reactant, and then the products will become less. So you first increase Cl2, thereafter Cl2 will decrease and PCl3 will decrease. So after that, can you see Cl2 decreased, PCl3 also decreased, but since the reverse reaction is favored, PCl5 increased, so it started to increase afterwards. So you first have the initial spike, then after reactants increased and products decreased. Right, and then the last one, 10.7, which external change in the system is responsible for the change in concentration of the species in the mixture? Now, since we know that we have changed concentration, it means you could have something changing in pressure or even in temperature. So any one of those external changes could have caused the concentration to change in the species.